Good afternoon, everyone. How's everyone doing? Did you have a good break? Yes? I hope you're fully charged now to continue and to finish. We just have one more week, and then that's it. So we need to get organized. Let's start talking about the exam. The exam is going to be it's going to be the final exam on the date of the final exam as said in the registrar. But it's not going to be comprehensive in the sense that I'm not going to ask you details about what you have already did in exams 1 and 2. It's going to be mostly about hydraulic fracturing, okay? But at the same time, you need to know the basics of, for example, how to calculate a vertical stress, a horizontal stress, a pore pressure if given an overpressure parameter. You need to know also in a wellbore in which location you would expect to see a hydraulic fracture or a breakout tube. That I think you did very well in the previous exam. All of that basic knowledge, you have to know that for the third exam. But I'm not going to ask you details about the previous ones. I cannot give you a copy of the final exam, but I'm going to give you a list of topics that we're going to see, okay? And I'm going to upload that today. So we can discuss a little more about the exam, but probably you'll have more questions next week on our last day. And just prepare for that day so you're ready to ask questions by then. Homework. You have a homework now due next Monday, and it's going to cover homework 11 and 12. And these are going to be the questions from 5 to 8 in chapter 7 from here. So let's go over here. You already did 1 to 4, and now you have to do 5 to 8 for next week. And today, hopefully, you will get everything. You will see everything you need to finish 5 and 6. So I strongly encourage you that after today, you try to solve 5 and 6. And then on Wednesday, we talk about 7 and 8. And also on Friday, and then you're done on Friday. And then on Monday, we have a sort of a review, and then you submit your homework. You study for the exam, and you don't hear about me anymore. Okay? All right. So I just wanted to tell you, too, for organization, that on Monday, we're going to have a regular lecture in the sense that we're going to meet here. Hopefully, we'll cover everything, so it's going to be more like a review. But also, I'm going to have in this same room an invited lecturer at 4 p.m. from Equinor to talk about geomechanics and hydraulic fracturing. So you're also invited to. I'm going to send an email later on. And I think that's it about organization. Do you have any question? Everything is clear? Okay, well. Then let's talk about content. And for that, I know that it was a long break. Any funny story from the break? Anyone did something fun? Skiing? No? Yes. I went to Vegas and to Grand Canyon. That was very nice. That was very nice. I didn't go skiing, but hopefully I'll try to do that next year. Okay. All right, so hydraulic fracturing. We have seen hydraulic fractures in nature very quickly, but then how we use them in well testing. like a leak-off test or in the defeat test. And then for the step rate test, when you want to inject something. Then we continue on hydraulic fracturing design. And something probably I didn't specify a lot, that was that in hydraulic fracturing design, what we want to determine is what is going to be the length of the fracture, how far is it going to go out from the wellbore, what is going to be the height of the fracture, and also what is going to be the width. Because with all those properties, at the end, what you want to do is you want to design a hydraulic fracture so that you can predict what is going to be the productivity of a wellbore with a hydraulic fracture. If you know what is the fracture half length, the width, and again the height, if it is a 3D model, you can predict what is going to be the skin factor and how much productivity you're going to have, and what is going to be the improvement over a regular wellbore. And having a fracture, it really bumps up the productivity a lot. Just imagine that if you don't have a fracture, all the fluid flow has to go through this small surface that contacts a wellbore with the rock. And that's generally very small, right? It could be like just the surface of like those wellbore images that you see over there. But now you have a fracture that goes from here to ECJ. That's a much higher surface area, and that's going to help the fluids get into the formation a lot quicker. So we are trying to see what are the fracture length, fracture height, and fracture width that results from injecting fluids, and we started that with these models that we mentioned. So let me come back quickly over here. First of all, we talked about what is the mechanics of a hydraulic fracture, coupling the fluid flow and the deformation of the rock, and also how it breaks. And once we put all of these together and we do a little bit of math, we get to put together these models that we didn't talk in detail a lot last lecture, but I'd like to spend a little bit more time today just to finish this up. Basically, these models, what they do is they couple everything. They couple fluid flow within the fracture. They can tell you what is the fracture gradient between the wellbore and the tip of the fracture. They also capture how much the earth is opening, and that tells you the fracture width. And as you may expect, the amount of fluid flow that goes through a fracture is going to be proportional to that fracture width. It's going to be inversely proportional to the viscosity of the fluid. So when you put all of these together, you can arrive to these equations of fracture half length, net pressure, and fracture width as a function of time. So let me switch here to my notes over here that are a little bit more developed than what I have over there. But again, everything is here, and it's relatively short, so I recommend that you read all of this, and we get to these models that we mentioned before. Let me make it a little bit bigger. These three models, PKN, KGD, and radial models, they model single fractures. And again, they tell us how the fracture is going to propagate. Let me tell you now, before we continue, that these models are relatively old, from the 70s, even before that. And by now, we know that hydraulic fractures can be a lot more complex than we did before. And in general, they are not going to be that simple planar fractures. And we're going to see later on what is the role of, for example, a shear reactivation near a fracture that also helps a lot to produce more fluids out of the formation. But by now, let's just stick with this conception of a planar fracture, although remember that sometimes this is a very simplified fracture model. Okay. Again, you put all the equations together, and then you can recover these three equations that tell you fracture half length, fracture width, and net pressure as a function of your parameters. For example, injection rate, plane strain modulus. I'm going to talk in detail about what is that today, and you'll see how useful it is. Viscosity, fracture height, and I don't think I missed anything. And then time. And these are all for constant injection rate. If injection rate is not constant, then this is going to be different. All right, so problem number 6 in the homework is about using these equations and predicting what will be fracture length, width, and net pressure with a given injection rate and viscosity and so on. So I recommend that you solve this problem with Excel, because it's going to be very easy here sometimes to miss one of those powers. So just do it with Excel. Let me go to the problem. This is number 6. So here you have a fracture height. You have what is the stiffness of the rock. Remember, the double M is a million psi. So this is 10 to the 6, 8.9 times 10 to the 6 psi. Here you have an injection rate. Remember that we said that that constant, or that parameter I, there was a single wing injection rate. So you're going to have to divide this one by 2. And then you have to compute what is fracture half length, width, and net pressure. And after that, you need to do a little bit of volumetrics to tell me how much amount of water, given that volume, how much amount of water and how much amount of sand you need for that location. So it's just simple math, the second part. For the first part, you use the equations of the PKM model. And for the second part, you use I'm sure you can figure this out, it's just volumetrics. Important thing over here, try to convert all your units to the SI system, because these equations, when you get to all these powers, it's going to get very, very complicated unless you have some other factor here takes into account units. It's going to be very complicated to deal in field units. So put everything in kilogram, meters, second, and Newton, and Pascal, and then you'll get the right answer. So again, for this problem, I recommend that you do it with Excel, but verify manually at least the last point. In this problem, you have to compute this. Let me read again. I want you to plot this as a function of time for 1 hour. So do it, say, every 1 minute and get 60 points or less. That will be even fine. But for the last point, do it manually. So just make sure that you know how to do that. So if a question like that appears in the exam, you know how to handle that. But it's a very simple problem. Again, it's just about hydraulic fracture design with a simple model, and with that model you get what is fracture length and what is net pressure. And for a long time, this was what it was done to design a hydraulic fracture, and it worked more or less well. Today we have different completions and different more advanced capabilities, but the basic is similar. Okay, so this is the end of this section. And again, I have the questions here for PKN, for the KGD model, and for the radial, I don't have them here, so don't worry about that. There was something in the previous part in here, let me come back to the notes over here, that was assumed constant here and there, but that we didn't say how to calculate that, how to see that before. Do you see what that is? What parameter is not, was just defined just de facto without any property of the rock or nothing so far? What? No, no, that was the one that we didn't use. In this model, that's something important. It's a simplified model. We don't take into account the strength of the rock. So there is no toughness in the equations. But something that we didn't talk about much was what is fracture height. And that's what we're going to do now. Because that's something that we need to, if we use some of these models, that's something that we need to predict a priori. And there is a procedure in order to do that. Okay, so let's talk about fracture height. And this is going to be linked to something that we have already seen and have already more or less used a little bit. I think it showed up in the 2 exams, if I remember correctly, but at least in 1. And these are the stress logs. All right, so in simple terms, the fracture height is going to be defined by how the properties of the rock and the stresses change with depth. And let's see an example, for example, in which we have 3 layers, and I have one layer which is a stiff carbonate over here, and then I have a soft shale. So let's say this is stiff carbonate, and this is a soft shale. How can I measure the properties of rocks in the subsurface? How can I tell if the rock is stiff or not without taking any samples and doing any laboratory tests? The what? The density is going to tell you the mass density, but it's not going to tell you how stiff the rock is. So you would use a sonic, right? So we can do a log of this formation. Let's say we have an horizontal well, and we can measure, for example, the sonic velocities, or what is used in the field is a travel time, where the travel time, which one is longer, shear wave or P wave? Shear wave is going to be longer, right? So P wave is faster, so travel time is shorter. So let's say that travel time, it does something like this. And Also, you can use the shear wave. And measure what is the travel time of that formation. So longer travel time, that will be softer. Well, if you have these two, you can also compute what is the plane strain modulus. And the plane strain modulus is a property that depends on the Young modulus and the Poisson ratio. Usually in subsurface applications, we do not, almost we never use just the Young modulus by itself. It's always combined with the Poisson ratio because it's under a state of loading which is not just in one direction and unconfined in the other one, but it is confined in the other two. And I'll explain why we have this in a bit, this plane strain modulus. But this is just telling you how stiff the rock is. And with these two, and with equations that we're going to see in a bit, you can calculate what is the stiffness of the rock. And probably in this case, as we were saying, this is going to be stiffer, and when it gets to the shale, we're assuming it's going to be softer. All of this is with depth. Okay. Basically, to go from here to there, we just apply the equations of elasticity. Now let's say that in this layer system, I apply a tectonic strain. You guys remember that tectonic strain was this strain that made the horizontal stresses change and were proportional to tectonic activity. In strike slip or in reverse faulting regimes, we have more compression, so one of the stresses was higher than the vertical stress. On normal faulting, these were less than the vertical stress, but tectonic stresses in different directions, say north-south or east-west, could make the stresses change direction and have SH mean different than SH max. Let's assume that we are, in this case, trying to predict what is the minimum principal stress. And the minimum principal stress in this case is applied in this direction, and we're applying a tectonic strain that also goes in this direction. Where do you think the stress is going to be the highest? In the carbonate or in the shale? If you remember, just from basic elasticity, stress is proportional to stiffness. So if we apply the same strain in the entire sequence, then what is going to, this is going to be the same, but if this is not the same, stress is not going to be the same. So in this case, stress is going to be higher in the stiff carbonate than in the soft shale. Now, as a result, I'm going to have a variation of minimum horizontal stress with depth. And this is something which is called mechanical stratigraphy, and it also involves the variations of the properties of the rock. So this rock may be stronger than this one, and that added together with the variation of stress yield this mechanical stratigraphy. All right, so we're very close, and now just one more step. Now what we're going to use this in order to define what is a fracture height. You remember that we always said that a hydraulic fracture is going to grow perpendicular to the minimum principal stress because that's the most energetically favorable condition. Why would you push against a stress which is higher when you can push against a stress which is lower? And the same principle is going to apply here, in the sense that if you were to start a hydraulic fracture here in the middle, and this one starts to grow up, at the beginning, the hydraulic fracture growing out of the page is going to grow similar to the radial model, in which it goes up in this direction, it goes down, and also it goes front and back. We can't see the back. But now, more or less, the state of stress is the same in all these regions, so it just grows radially, as we have seen before, because it feels that everything is the same in this region, but it's going to reach a point at which it's going to see that there are layers with higher stress. And now the fracture, it might go onto these layers, which have higher stress, or might continue propagating on the soft rock, but now instead of growing up and down, it will just grow in this direction, and it will grow always within the soft shale as long as the net pressure here it has to be smaller than this contrast. So if the net pressure were to grow up and exceed this amount, then it could go into the other layers. And for example, then at the point in which the net pressure in this location is higher than the initial contrast, it could grow into the other layers and find some other limit in the fracture height. But for now, let's just limit this to that. And if we keep the net pressure within those limits, then this is going to be the hydraulic fracture height. All right, well, this is a very simple example, but the concept is very simple. It's just in some conditions it may get a little bit more complicated. Do you have any question about this? So again, the hydraulic fracture is going to be limited by stress contrast. That's the main factor that controls fracture height. In some other cases, also it may be the property of the rock, but that's a second order effect. All right, so let me show you a real case. And this is actually what you have to do in problem number 5. You have to determine this stress log on your own. Okay, so let me get there. And before we get there, let me tell you what, let me show you what I was saying before. So, oh, by the way, I uploaded the solution to the exam, and I have your exams here, so I'm going to call your names after we finish the lecture. But in meter number 1, no, I guess is, let me see. Why don't I see a preview of that? Okay, it should be this one. Okay, so in this case, this problem, this is in a stress log. These stresses will figure out the same way that we're going to see now, but with a little bit of a more complex mechanical model, assuming anisotropy and a few other things. But this is our ultimate objective. In the same plot, to plot pore pressure, vertical stress, and the horizontal stresses. And with that, if we know where the perforations are going to be, or well, actually we can say where the perforations are going to go in order to fracture the intervals that we're interested and determine what is going to be the fracture height. All right, so I have a more simplified case over here. We already discussed this over here. And okay, so the first step is over here. And let me go to the problem. In number 5, you're going to have to download this file, which I don't have the link over here, but let me try to find it quickly. Okay, I'll upload, and I will put this link over here, but if you go to undergrad homework number 11, you have this file. And I'll send you the link for this. And when you download this file, here you have depth, reservoir pressure or pore pressure, density, and travel times, and also porosity. So with all this data, what you can do is, with density, you can calculate what is vertical stress. This is a place onshore, and it starts at 1750 feet. So you can assume everything above that has the same density as this point. So you have density, you can calculate vertical stress. You have travel times, you can calculate the plane strain stiffness of the rock, which is, you're going to get it from these equations. With travel times, you get velocities. With velocities, you get Young modulus and Poisson ratio. These are what we call dynamic Young moduli and dynamic Young modulus and dynamic Poisson ratio, because they are measured with waves. But what we see in practice is that many times the actual stiffness of the rock is lower than what you measure with waves. Usually waves measure higher stiffness because it involves a very small strain. And when you make a fracture, when you deplete the reservoir, the stiffness tends out to be lower. And that's why there is this conversion factor from dynamic to static, which from what we said before, it's less than 1. So you multiply your Young modulus found dynamically times this factor, and then you get your static Young modulus, which is a better approximation of the stiffness of the rock. Usually this conversion factor you measure in the laboratory. You do measurements both. The ones that, for example, we did in the laboratory, loading the load directly compared with wave measurements, the ones that you did in petrophysics. I don't know if you remember, but you can measure P wave and shear wave with ultrasonic measurements. And so once you have those two, you make a correlation and you get this factor. All right, so, and once you have that, you are here, then you can calculate the stresses. How do you calculate that stresses? Does anyone remember? And this is something which is going to involve something that you already know, and you're going to need to use it again. Okay, let me motivate you a little bit. Who wants extra points? and you will have to answer correctly what I just said. So what do we use in order to get from here to horizontal stresses? I'll give you a hint. It was, far, far behind from what you have seen. Yes, Ms. Ruhana.
Are they tectonic strain? Those really long ones that give you sigma H max and sigma H min? And
Yes.
you add it to core pressure to get the S1, S2.
Correct. So you see with these stress logs, we get vertical stress, then we get stiffness of the rock, and if we have a tectonic strain, we can calculate what is going to be the stress. And let me find that equation. I think I have a link over here, 332. These are these long equations that now we can see that they tell you what is going to be. Let's use the ones for sigma H max. Epsilon H, the plane strain, the rock, or the plane stiffness. Sorry. Okay, so and now we can actually close the story, because if you remember, I told you that we didn't actually know what these tectonic strains are. And some of the problems, I just make them up or I get them from other data. But so far, I have given to you this tectonic strain. I didn't explain where they come from. Well, these tectonic strains, they come from, let me find that again. They come from the calibration of real data with the stresses that you calculate with those equations. So for example, test, which are these, what is SH mean, so that your model matches the observed data. If you had breakouts are going to tell you what is the value of SH max, because the higher the SH max, the higher your breakouts are going to be for a horizontal wellbore. So that's going to help you calibrate the second one. And the more field data that you have, the better your model is going to be calibrated. And by finding what those tectonic strains are, you can develop what is called a mechanical earth model that is going to allow you to predict stresses outside the range of where you did your tests. For example, you may have done your defeat test here, but you don't know what the stress is over here. That's why it is helpful to do these studies of mechanical stratigraphy, see how the property change, so you will predict how stresses change along the entire formation. Okay, so last question. Let's say that we decide to fracture this wellbore, and this is a vertical well starting here. Anyone wants to answer how far the fracture will grow? And again, I'm going to give you some extra points. So let's say that this is 300 feet, okay? So just by eyeballing, what is going to be more or less the height of the fracture, Mr. Ali Ismail?
I was going to say that up until the two peaks, NSH min and NSH max.
Up to that?
Yeah, and the one at the bottom.
Why do you say that?
Because it looks like a
Yes, I hope all of you, you can see that, but now this is a more realistic version of what I had over here. Let me find that. All right, it's a more realistic version of this, where your stress has a local minimum over here, and it increases up to there and there, so that if you were to start a fracture, probably at a relatively small net pressure, it will just stay around here. If you overcome that net pressure from here to there, it can even go to places in which the minimum principal stress is vertical. But before we do that, so the answer is the fracture will just stay mostly around this area. So if we had an entire pay that, for example, goes from this the top square to the bottom, and if you just fracture here, your fracture is not going to grow all the way down. It's just going to stay there. So you need to take that into account when you do your fractures. Probably you want to do another perforation somewhere over here, because otherwise it's not going to go down. All right, so let me put the points to Mr. Al-Ismail. And now the other question. This one for double extra points. Double extra points, yes. What happens if net pressure gets to somewhere over here, where the minimum principal stress is not it's not horizontal anymore, now it's vertical? So let me see if I can recreate this in here. So think about that. And we're saying that this does something like this. And what happens at this point if the fracture continues propagating? So let's say that we start the fracture there. So this one will grow, will grow, will grow, and then when it finds this point, if it continues growing,
The fracture will turn and start opening vertically?
yes, and it will do something like this. And that's what is called a T-shaped fracture. And if you remember from the discussion that we have of hydraulic fractures in nature, those do occur, and well, in nature the vertical fractures are called dikes and the horizontal ones are called seals. But this can also happen in hydraulic fracturing completions, and in general it's not desirable, because in most cases you want your hydraulic fracture just to continue for the long distance, for the distance that in which you have your pay. If at some point within your pay you have some of these high stiffness barriers, they may limit your fracture, it might not grow anymore. All right, so now if you put together these concepts of hydraulic fracture height, this is a simple one, but now if you consider the effect of the net pressure and when it will continue growing or not, or if it will turn or not, that's and you add this together with the equations that we have seen and with the models that predict what is going to be net pressure and fracture length and all of that together with something in which you do not set what is hydraulic fracture height, but you calculate it as you go, that's everything that you need in order to make a hydraulic fracture simulator. It's not that complicated. It's just that. It's predicting, having a good grasp of whether stress is as a function of depth, seeing what's your net pressure, if your net pressure is going to go over or not, and if that's the case, what is going to be the new shape of the fracture and where the fluid is going to go. So here I have one example in which we have a prediction of what is the minimum principal stress. We see that varies as a function of depth. And in this case, there are perforations at this depth, 2,100 feet. And what this hydraulic fracture simulator predicts is that because stresses decrease as you go up, if you start here, the fracture will not go down, but will rather go up. And I hope that you can see that the hydraulic fracture is going to open the most where you have the regions where the stress is the lowest. So in all these local minima of stress, your fracture is going to be the widest. And also is in those locations where the fracture is going to be the longest, because width and length are more or less related. The bigger the width of your fracture, in general, the longer it's going to be. And so these two regions of low stress are these two regions where the hydraulic fracture is the longest. So just to clarify, this is a cross-section of the fracture at the wellbore, and we see the width. Here, this is a side view of the fracture, where this is the plane of the fracture, and you can see how hydraulic fracture height is not the constant anymore, but varies with depth, because we have now put this more complex variation of stress with time, and where hydraulic fracture height is not a constant anymore, but now it varies. But it's just that. You put fluid flow into this model, couple that with the equations of mechanics to predict width, and you get a hydraulic fracture simulator. Let me show you one more example, and with that we'll finish. I always get it wrong. Let's see if now I get it right, the one I want to show. No, I'm misspelling it. Wait. G-O-H. No, how do you say?
I think it's G-O-H.
Are you sure? No. Okay, let me, I'll remember, but let's go to this other one. Okay, so in these hydraulic fracture simulators, you see this is what you do. You get a stress log, you predict what stress are going to be as a function of depth, and with that, you can predict your fracture height and your fracture width. And the equations that we have seen are exactly the same that these softwares they use. And if you want to use this for multiple hydraulic fractures, you can do it as well. And we'll see that example on Wednesday, okay? I think it was GHO. That's how it is. GOH. Okay, I'll find it. All right. Okay, guys. I'll see you on Wednesday. I have your exams here.